Hello everyone. As Panky said, I'm Fernando Dominguez, and I'm come here to talk about code similarity analysis with Radar and Diaphora. Up top in the presentation, you have a link to Google Slides, so you can submit your questions if you have any during the presentation. I may not be able to answer them during the presentation, but I'll make sure to address every one of them at the end. So yeah, let's begin. Okay, so a bit about myself first. As well, you already know my name. I am a malware analyst and security researcher at AT&T Cybersecurity in the Alien Labs team. Please increase volume 1 second. Hopefully it's better now. Yeah, so as I was saying, I'm a malware analyst and a security researcher at AT&T Cybersecurity in the Alien Labs team, which is the security research team. That down there is my Twitter link if you want to follow me or send me some questions. The direct messages are open. And yeah. So the objective of this talk would be to describe the process I followed when porting Diaphora to Radare and MySQL. If you don't know what Diaphora is, this is extracted from the GitHub repo, the original GitHub repo, which is linked there in blue. So as it says, it's the most advanced program diffing tool. It works as an IDA plugin and was released on SysCan 2015 and it's actively maintained today. There was already a port that Pancake did back in 2017, and you have links here to the port and to the presentation itself of the port, but I will talk about more this later. And why we wanted to port Diaphora or port or to update the already existing port. It's because there are of course many reasons, but for our use case it was part of a bigger project which I'll describe now. So the bigger project, if you are familiar with Intesser, it's the easiest way to explain the bigger project would be like it's we wanted to build a similar system to Intesser, and if you don't know what Intesser is, it's a platform that does malware identification based on code similarity. So you submit a sample, and it tells you this sample is family X because I have seen code that I have registered in my system that it's from this family. We were mostly focusing on IoT malware, and this is because this project originated from a necessity where we had a lot of undetected Linux samples, which were variations of open source families, because there's so many threat actors actively modifying open source code to create their own variants that static signatures break a lot, because all that modifications, your signature may not match them. So yeah. Also, we were taking advantage of the fact that in the IoT landscape, packaging is not usual. So that's a problem out of the way in code analysis, and it would be easier to find the matches on not packed code. Okay, and this is a schematic on the over how this project would work. It could have two phases, two processes different. The first one you need to do it before the second one, and it's a new sample that it's unrecognized to the system arrives. So this sample is sent to the analyst, and the analyst would then identify some indicators for this sample, that can be either functions or strings, and then those indicators are saved to a database with Diaphora. Then once you have more or less this indicator database built, you can start accepting samples and then generating their Diaphora database for that sample, and then you compare the Diaphora database for the sample with the indicator database. So then you would get code matches across the two databases, and of course get the family identification for that sample. Okay, so as I said, Diaphora already exists and works perfectly fine as an IDA plugin. Why we wanted to move from IDA to Radar? Well, first of all, because it's an open source project, so we can modify it and bend it to our needs. And also because it's free, and IDA would be quite expensive, especially if you consider, because we wanted to support a lot of different architectures that are common in the IoT world. And IDA, if you sum the cost of IDA and all the compilers for all the architectures, and would sum to quite a hefty operation price. And also Radare has excellent support for many different architectures, so that's more than enough for our needs. And why also? Because the original Diaphora works with SQLite databases. This would be over MySQL or a similar database. I'm using MySQL now. Why that migration of database engine is because, as you may recall from this slide, there are multiple analysts that are all writing to an indicator database, and sharing a database over SQLite is difficult because it's not a database engine that's made for sharing. And yeah. Also, if the project were to be successful, we wanted to also build web services on top, and web services have worker threads that access the database. Yeah, that kind of databases engines are more robust for concurrent access and that kind of usage. Okay, so problems that I faced when porting when updating the port, the existing port, was that first of all it was Python 2, which has been end of life now for almost 2 years. It was done with Diaphora version 1. Current version is version 2.06, I believe, which added a lot of new detections algorithms, and we wanted to take advantage of those. That, of course, it worked with SQLite, and some features were incomplete, like, for example, it wasn't decompiling the code, it wasn't obtaining the CFG hashes, of course, because also the Diaphora 1 didn't use those, I think. And it was missing some information about the functions, like switches and topology and related. So first steps on porting this code was to update the Python 2 bits to Python 3, and then I began changing all the SQLite specific dialects to MySQL if there was an equivalent, and then began running the script once and again, until the crashes stopped and I got a database with the binary information. But there was a problem, and it was that the first time that it worked, I don't remember exactly how much it was, but it was, I think, around 30 minutes for it to analyze the sample, which of course it was way too much, and that was not usable for us. So of course the only option there was to optimize the performance of the script to make it run on a reasonable time. Okay, so for optimization, my first approach was to log every command executed, issued to Radare, executed by Radare, and log its execution time and see if there were any kind of commands that were taking longer than others. But what I did not foresee was that I generated a 1,000 very long log text file. So that was a bit hard to analyze because, reading all those lines and hard to get information out. At least I drew some conclusions from that, and it was that a lot of commands were being repeated. And the solution for that was to implement a cache in R2pipe, which actually Pancake did that. The cache, if you want to know how to use it, because I think it's fairly new and I don't think it has been made to the docs yet. But it's like so, you just open a file and then set the use cache flag to true. And then from that point onwards, how it works is very easy. It has a Python dictionary, and if a command has already been executed, it returns the result from this Python dictionary, and if it has not been executed, then it issues it normally. The cache does not invalidate by itself. You have to invalidate it by hand. The function to call is this one, invalidate cache. Would probably be a good idea to call it if you make modifications to the binary. If not, I don't call it, and it's perfectly fine. And yeah, and that gave us a speed up increase of about 5 times. Of course, this depends on your use case of R2pipe. In my use case, I was repeating commands about 5 times each, and that's why you see that increase. But yeah. Other thing I did, related to the log file previously mentioned, was to use R2pipe in native mode. Oops. Looks like something crashed. As I was saying, the other thing I did was to use R2pipe in native mode. What native mode means, if you don't know, it's that Radare, if you use R2pipe, normally what you do is span a Radare process, which is separate from the Python process, and then the two processes communicate through a pipe. If you open R2pipe in native mode, what it does is that it opens Radare as a dynamic link library, and it loads into the Python process, and then for each command that you want to execute, it does a SQL to a function that executes this command. Of course, this method is faster than the regular pipe communication, and in my use case, it gave me a speed up of about 4 times. The only downside to this form is that if Radare would be to crash, then you would the whole Python process would crash because it's loaded as a dynamic link library. But anyway, if Radare crashes when using the pipe, you are probably gonna get stuck into the R2pipe CMD function, so it's not that big a downside. And with these two improvements, I didn't mention the R2pipe in native mode can be used by a perpending C call to the path to the binary, and then you are golden. And as I was saying, with these two optimizations, I managed to go down to 1010 seconds for the test sample. It's still a lot. I think it's more than 15 minutes. So yeah, further optimizations were needed, and because this logline was too big to draw any real conclusions from that, I moved to another approach, which was using PyInstrument, which is an instrumentation framework for measuring performance of Python scripts. And yeah, you can see here that for this run it was the previous time, 1010 seconds. This of course is the starting point of the last slide. And here you can see that the main bottleneck is in the save function by 4. And this is because, well, the save function does the database access, so it saves a function read from the binary to the database engine. And this is because I forgot to create the table indices. So yeah, I was reminded by this, and then I created them. And next slide, you can see that from 900 seconds it went down to 51, which is quite an improvement. So yeah, don't forget to create your table indices. And now here you can see that the main bottleneck of the script is in res function, which is in the Python code the function that reads a function from the binary itself. And within res function the main bottleneck is getFunc. GetFunc, all it does is an AFI command in Radare. And AFI is, this is how I discovered that AFI is quite a slow command. So the conclusion was to attempt to substitute any and all usages of AFI for something else. In my case, I could replace them all. And I think it's in mostly any cases you can replace them all. One thing I did that may be a bit counterintuitive is that instead of calling AFI, you can call AFLL, which gives information from all the functions and similar to and gives similar data for AFI, and then you cache that information either by using the R2 cache or yourself by hand in the Python code, and then that's you only call that command once, and then you have almost all the information that AFI for each function would give you. So yeah. Once, by the way, we are down to 143 seconds for the whole sample to run. And yeah, as I was saying, if you remove every getFunc or AFI usage of the function, then I reduced it to 77 seconds, and now the main bottleneck is guest type. Guest type is the decompiler, although with that name it's not very, you know. But that's what you would expect, right? That the main bottleneck in one of these scripts is the compiler, because they are usually the slowest parts on any disassembling software. And in my case, I'm using the R2 Ghidra decompiler, which is also known for being a bit slower than others. And here, for that particular bottleneck, the compiler, we can do much. Well, the most we can do is to substitute the R2 Ghidra decompiler for another decompiler, if you want to use the decompiler, of course. And for example, I tested with PDC. You can see here that R2 Ghidra is taking 17 seconds for the whole binary to decompile it, and with PDC it's quite faster. It takes only 7 seconds to decompile the whole binary. And yeah, also bear in mind that the PyInstrument instrumentation framework also adds a bit of overhead. So the real executions times would be more like 20 seconds down what says here. So for PDC about 40 seconds to analyze the sample, and for R2 it would be it was 77 seconds, so about 50 something seconds. Okay, and then further optimizations, because those previous times were already acceptable for us. Of course, the IDA version runs faster in, like I said, 15 seconds for that particular sample, and further optimizations can be made to match kind of these times. But I decided to stop there optimizing and continue in a near future. And on the meanwhile, I did some other thing that can also help reduce the time, which was to add FLIR signatures to detect library functions and skip them, because usually you don't want to analyze and find matches across these statically compiled library functions. So how it works is you can put any number of .sig files on this directory here, and they will all be used to scan the binary at the startup, and any function that matches those signatures will be excluded from analysis. And by default, I have included in my repo these signatures that you can find here. They are signatures for the usability function library. And I bundled those because for my use case, as I was analyzing IoT malware, uselibc is a common libc implementation found in IoT malware. So yeah, but you can feel free to change them or remove them. This is an optional feature, by the way. It can be also turned off in the command line. So how do you use it? As this fork of the code uses MySQL and Radare, you need those installed on your machine. Well, Radare, you need to install it locally, and then the MySQL server can be remote or local. Once you have the setup done, you can go to this file db.json and then fill in there the credentials for your MySQL server, and then the only thing left would be to install the requirements for the script itself. Once you have all that, you can run the script. It's pretty straightforward. The only thing you need to do is to, if you pass it a single file, it will analyze that file, generate the Diaphora database for that file, and exit. The database name will be the SHA-256 of the sample to avoid collisions in names. And if you send two files to the script, it will analyze both of them and generate both databases, and then compare the databases using the Diaphora algorithms. Then some options: if the default behavior, if the database already exists, is to skip the analysis because it's already done. But if you, for whatever reason, want to force to generate the database again from scratch with the -f command line option, you can do it. Then if you provide two files and the comparison is performed, the default option will be the default output will be an HTML file. The original Diaphora, what it does is that it shows you the results in IDA directly in a window. Of course, we don't have that here, so this is what I did to visualize the results. And the default name for this file will be the first 10 characters or the first file's hash,
underscore vs underscore and then the first 10 characters of the second file hash .html for of course, and with -a you can disable the skipping of the library functions. So by default it is being done. With -a everything gets analyzed. And now I have prepared some demos. The first demo uses a Sakura sample set. Sakura is a Graphkit variant. It's not particularly special or interesting or anything. It's just yet another Graphkit variant. I chose it because it had one debugging symbols, and also it was one of the first variants that I came across while I was developing this project. So this is my sample set. If in case you want to reproduce the results or try at home or whatever, they are, as you can see, they are all ELF files, and there's a bunch of different architectures in which this bot is distributed. And this is the easiest comparison. It's I did it as a basic test to check that everything was working correctly. And for example, in this by the way is the generated HTML file. And this you can see here that we are comparing this Sakura sample, which is an ARM sample, to this other Sakura sample that it's also an ARM sample. And you can see some stuff. That first of all, these functions here, it says that it matched them 100% of the code in them, and it's because the matching description says that they have the same clean pseudocode, but it's also they are also very small functions, which just one basic block each, and probably they are also small in size. So maybe these functions are wrapper functions or just a jump or something similar, and it's being matched because they are very small. One thing you can do to fix this in case they are not real matches or that you don't want to match these kind of functions is to only analyze as the same as being done with flirt. You can also add a condition for a minimum number of basic blocks, for example. That's still not being done in the code, but it's very easy to do, and I'll probably get to it in the coming days. But for the rest, you can see that they are very nice matches. The ratios are very high, and you can check they are true matches because, as I said, both samples have debug information, so you can see the function names, and you can see how the matches both have same names and the same amount of basic blocks. So yeah, you can check easily that those are true positives. Moving on, then a bit of a harder test. This time we are still comparing within the Sakura sample set, but now we are comparing two different architectures. Here we are comparing an Intel x86 sample with an ARM sample, and now you can see this in the results that first of all the number of matches that previously was 40 has decreased to 18. Of course, across architectures it's harder to match functions, and also that the ratios have gone down, but this is to be expected because now that the functions are different architectures, they are gonna be more different. But still, you can see that the results are very nice. Again, the names are the same and the basic blocks are the same, so we can easily assume that they are actual matches. And lastly, this would be a Sakura
sample in 864 compared against Yakuza, which is another Graphkit variant sample, ARM also, so cross architecture and cross variants. And still the number of matches, of course, continues to go down as it is expected. The ratios kind of maintain themselves in about 0.75. And again, the matches, you can check that the names are the same, basic block are the same, so we can conclude that it's able to produce good matches across variants and across different architectures. So that's it for the first demo. And now a second demo. I thought, when I was writing this project, I came across this blog post from Maptics, and there you have the link if you want to read it for yourself. Also, by the way, this demo is done with the bigger project I was talking about previously, not with the R2 Diaphora, although the bigger project is mostly a layer on top of it to ease the process that I was describing previously. So yeah, as I was saying, the blog from Aptics, they claim that they have found Mirai code from the Mirai source code leak in some Graphkit samples, and they showcase this hash, this sample that's also extracted from the blog as a showcase that their findings. So now here we have some screenshots also extracted from the blog for their claims. They say this is the Mirai source code or part of the Mirai source code leak, and these windows that have Graphkit on them are the sample that I was referring to in the previous slide, this one, that if you recognize the window, it's the hex race, the compiler. And yeah, they say this source code highlighted in yellow has been found in Graphkit samples here and here. Oops. Okay, so I thought it would be fun to test these claims with my own project to see if I could also see these findings on the sample. So what I did was I downloaded and compiled the Mirai and Graphkit source codes, the leaks, and in every architecture they are usually distributed. And then I added the most prominent functions to the indicator database. And by most prominent functions, I just mean do not add like we saw previously a wrapper function or a library function, something identifiable enough that can generate meaningful matches. And then I ran the R2 Diaphora script comparing the database generated for the blog sample to my indicator database, and the result was this. I got 9 matches for Graphkit, which I have excluded most of them because they were not meaningful for this presentation, and 1 match for Mirai. And if you remember from the screenshot, these functions and TLS and holes and std that match Graphkit are the ones here that they say Aptic says it's Mirai. So I was getting this function match, but not to the supposed family that they should match, and I was getting a Mirai match, but another function. And if you have seen, if you are familiar with Graphkit and Mirai source codes, Graphkit is the naming convention on the function is usually camel case, and the naming convention for the Mirai source code is usually a snake case. So it makes sense that these functions are actually Graphkit, and this function is actually Mirai. Actually, also, if you because among the first screenshots, there's a Saint HTTP function in the Aptics blog screenshot. If you look for that function on the original Graphkit source code leak, it's not there. But if you search this prototype from the just write it manually from the screenshot and search it on Google, you will end up in this link, which is among the first results. And if you visit the link, it says original Qbot, which is another name for Graphkit, modified by XFIFA version 4. So it's indeed Graphkit, those functions that they were previously claiming. But yeah, although it is true, however, that there was some Mirai code in the sample, just not the functions that they were claiming they were. Yeah, that will be all for the second demo. As for future plans, because the work on this project is far from over, on the near future I plan to keep optimizing the performance. I would like to match the performance of the IDA version. There's also a missing feature. The IDA version of the script obtains about 42 or 43 indicators for each function, and there's one missing in the current Radare version, which is the pseudocode primes hash, and this is because the pseudocode primes hash uses the abstract syntax tree of the decompiler. And for Radare, for the compilers I'm using Ghidra and PDC, they do not offer an AST, or at least they do not offer access to the AST. So for this to work, you will need to generate an AST from the pseudocode obtained with whatever the compiler you are using, which is doable, but a bit more work. And also, in general, the IDA version currently is generating more matches than my version. So yeah, I also plan to work on improving the quality and number of matches, and make sure it's they are all the matches that you can generate from the binaries. And yeah, also some random more usability features, like creating a pip package for easier usage and all that. If you are interested in the code, the link is there. Of course, it's public. If you want to contribute as well, drop me a line, write to me in Twitter, for example. And yeah, if you were interested in this presentation and thought it was a cool project or liked it, we are currently hiring in my team. Positions are not very yet official, so if you want to join or are interested or want to see what's there, by the time being, send me a Twitter DM, for example, and I'll move it. Yeah. Now, if you have questions or there are questions, I'll check the YouTube chat as well. Let me, because the previous, there's on Google Slides one question. Maybe you said it, but I lost for the string crash. Is this open source and published somewhere? R2 Diaphora is open source, yes. The code is here. You will have the slides available as well, I think. but it's as my name R2 Diaphora. And the bigger project, it's unclear yet if it will be open source or not. I will try to make it the open source, but since it's a company project, I would need to ask for permission to open source it. And yeah. Let me check if there are more questions in the stream. No, it looks like there aren't any. So yeah, I'll wait a few minutes, and if there are not any questions, that will be all.